So let's talk about a fundamental shift in how progress itself is happening. It's not just about technology getting a little bit faster every year. We're talking about a powerful, brand new relationship between artificial intelligence and the physical hardware it runs on. And this relationship, well, it's already starting to change absolutely everything. We're going to dive into what's being called AI's compounding cycle.
And this quote right here really gets to the heart of it. For pretty much all of human history, our progress came from building better tools, right? A sharper plow, a more powerful engine, a faster computer. But what we're seeing now is a pivot. Intelligence itself is becoming the ultimate tool. So imagine an AI that doesn't just use our best microscope, but actually helps us design a fundamentally better one, something that unlocks discoveries we couldn't even see before. That's the huge shift we're talking about.
Okay, so if intelligence is the new engine of progress, what's powering that engine? It's really easy to think of AI as just software, lines of code floating in the cloud, but every single bit of it runs on real physical hardware. And to truly get a handle on this new era, we have to look under the hood at the deep tech, the actual silicon and circuits that are the bedrock of this whole revolution.
All right, so first up, let's get into that hardware foundation. We're going to peel back the layers and look at where the real nitty-gritty innovation is happening right now, because that's where you find both the roadblocks and the incredible opportunities. So the source material points to a few key areas where things are really moving. First, you've got advances in just how we manufacture chips on a massive industrial scale. Then, people are completely rethinking these critical components called interposers. And maybe the most mind-bending of all, we are redesigning the transistor itself. The fundamental on-off switch that's the building block of all modern computing.
Okay, so here's a word you might not hear every day, an interposer. The simplest way to think about it is like a mini, super advanced circuit board that acts as a high-speed bridge, a communication superhighway between different chips, letting them talk to each other at unbelievable speeds. Making these things better is absolutely crucial for building the massive, complex systems that today's AI needs to run.
So it's not just about these big picture connections, right? We're also innovating at the most ridiculously tiny scale imaginable. We are literally creating brand new designs for transistors, and we're working at the angstrom scale. Now, to put that in perspective, a single human hair is about 500,000 angstroms wide. Yeah. And when you start operating at that scale, the world, well, it stops playing by the rules we're used to.
And this is where things start to get really weird. Our next section is all about what happens when we push up against the absolute physical limits of matter. Because as we shrink these components down smaller and smaller, we slam right into the wall of classical physics. The world just doesn't work the way we think it should anymore. So as we keep pushing, shrinking, optimizing, we are, whether we like it or not, stepping into the quantum realm. And I want to be clear, this isn't some far-off sci-fi concept. This is a very real, very present engineering challenge that chip designers are grappling with today.
This really lays out the difference. In our everyday classical world, things are predictable. An apple falls from a tree, we know where it's going to land. Simple. But in the quantum world, everything becomes about probability. An electron's position isn't a sure thing, it's more like a cloud of possibilities. And that means you can't just build a smaller version of an old transistor. You have to totally rethink how to build anything when the rulebook of physics has been completely rewritten.
And this is such an important point to grasp. We hear a lot about quantum computers, and that's its own exciting field. But the point here is that all of our most advanced, cutting-edge computer chips are now being designed and built in a world governed by quantum mechanics. Engineers have to bake that reality into every single future design, whether it's for a specialized quantum computer or the processor in the next phone you buy.
So we've got these incredibly powerful AI systems on one hand, and these massive, fundamental hardware challenges at the quantum scale on the other. This is where it all comes together. This is the single most powerful idea we're covering today, a self-accelerating loop of innovation.
So here's how this engine actually works. It's a two-step dance, really. In step one, we use our best AI to tackle the really hard physical problems, like designing a totally new kind of transistor or discovering a new material with just the right properties. Then, in step two, we take that breakthrough and we build the new hardware. That creates a more powerful platform than we had before. And that new, more powerful platform, it lets us run a next-generation AI that's even smarter, which can then turn around and solve even harder problems. And the cycle starts all over again.
This right here is the whole game. The source material calls it a tight feedback loop. But the key word, the one that changes everything, is compounding.
This isn't just steady, linear improvement. 1 plus 1 plus 1. This is like compound interest for progress, where the gains from each cycle fuel even bigger, faster gains in the next one. Each turn of this wheel makes the next turn happen faster and with a much greater impact.
So what does this all actually mean? Well, the ultimate implication of this compounding cycle is that the rate of discovery itself starts to accelerate. We're not just talking about getting slightly better smartphones every year. We're talking about a system that could speed up our fundamental understanding of science, from developing new life-saving medicines to creating clean, efficient energy sources at a pace we've never seen before.
And that brings us to the final, really provocative thought to leave you with. We are used to progress that we can measure in years or even decades. But what happens to our society, to our world, when the very engine of discovery starts upgrading itself faster and faster and faster? What does that future even look like? That's the question this compounding cycle forces all of us to consider.